So if you do not consent to being recorded, please leave now, and we'll get started. So my presentation this evening is on emergency power. And what is emergency power? Well, where were you when the lights went out? My wife's favorite joke. The answer is in the dark. So
depends on if it's daytime or not.
Emergency power is a way of getting us power in case of natural disaster, such as a windstorm. No idea when we might have one of those. My understanding is that Ogden and some parts of Salt Lake City were without power up to about 170,000 people after the storm on, was it Tuesday? So that was exciting. Our power only went out for 1 second, which was great. That's just long enough to kill the TV and internet router. We might have an earthquake, which could cut. Hello, dog. I have a dog here. He thinks I'm not paying attention to him, so he's going to jump on me. Sorry about that. Earthquake or other weather might cause our power to go out. So what else? We could be wanting to run in disconnected operation. For example, if it's field day, if you can operate on emergency power, that gets your team extra points on field day. Or you may be doing summits on the air or some other kind of contest where you are away from your normal shack or your normal environment where you want to do operation. So let's talk about emergency power. What is power? We had a class about this as part of our electricity and electronics class. We talked about power being the ability to do work. And this is a very physics definition, right? So in physics land, doing work consists of making something happen, making something move, making something change. The unit for power is watts. That's a very simple calculation. Typically volts times amps gives you watts. Volts are a measure of electrical pressure, or how hard the electrons are pushing. If you think of it as a tank of water, how high up your tank is so that gravity is pulling down harder, right? So that gives you your voltage, and amps are a measure of electrical current, or how many electrons are flowing. Think of that as being how fast the electricity is flowing through the wire, or the water is flowing through the pipe in the classic water analogy. Power is measured in watts, and it is how much work those electrons can do for us. Okay, so what do I need to power? In my emergency situation, what might I need to power? Well, obviously I need to power my radio equipment, because that's obviously the most important thing that is going to need power in such a condition, right? I might have a transceiver, I might have a tuner, I might have a rotor on my antenna, or something that needs power for my radio equipment. I might also have some other equipment. I might want a computer to be running. I might want to have a light so I can see my notepad to write things down. I might want to have some tools of some kind, maybe a soldering iron or power drill or something like that, whatever I might need to use to make sure my setup is safe and stable and secure. What other things might I want to power? Well, maybe the fridge or freezer. Might as well try to keep the food alive or dead or unrotted. I might need to power my cell phone charger or my handy-talkie charger or something like that. Might need to power a hot plate if I want a hot meal, or a microwave or something like that. A bug zapper if I'm up in the mountains and there's lots of bugs around, I might want a bug zapper, so get rid of those guys. In my case, I have an oxygen concentrator here at home for my wife. I definitely want to power that. So that's something that would be critically needed to have power. So we need to figure out how much power we need, right? So the first thing to do is check the wattage rating on your equipment that you want to power. So some equipment, like this generic power brick, has a tag on it that says it takes 20 watts DC. So it says it right on the tin, 20 watts for this piece of equipment. Some equipment doesn't have that. If it doesn't show the wattage, you can multiply volts times amps to get watts. So if I look at this laptop power supply, or this laptop has a label on the bottom that shows that it wants 19.5 volts at between 3.34 amps and 4.62 amps. So I'm always going to take the higher number, because who knows why it might want more in some cases, less in other cases. Maybe it has a CD drive or something, and the 4.62 amps is what the CD drive is running. But I'm going to pick the highest one just so that I know I'm not shortchanging myself. So if you multiply those out, you come out with about 90.09 watts, or we'll call it 90 watts for a typical laptop. This Kenwood D710, I couldn't find a good picture of the back panel that I could actually read and show, but in the manual it showed that the power requirements were 13.8 volts, plus or minus 15%. And for VHF and UHF transmit on high power, it needs 13 amps, or up to 13 amps. So on receive only, it's going to draw less than 1.2 amps. So if we figure 13.8 volts by 13 amps, we figure we need about 180 watts of power to run our D710 while transmitting. Now, it's obviously going to be less than that when we're just receiving, but again, we want to plan for our maximum power usage. The Kenwood TS480, they have two different models. They have the HX and the SAT. I don't know if you're familiar with these radios or not, but this is an HF radio. The HX is a 200 watt radio. The SAT is a 100 watt radio with an integrated auto tuner, antenna tuner. So on the HX, it actually has two DC inputs. It wants 13.8 volts on both of them. On the SAT, it only has a single DC input. On the HX, on DC1, it will pull 20.5 amps on each power supply if it's transmitting at the full 200 watts. On the SAT, it will pull up to 20.5 amps. And on receive only, or standby as it's called, less than 1.5 amps. So we're going to figure out for the HX, we would need 600 watts. And for the SAT, we would need 300 watts. And keep in mind, that's 200 watts of transmitted power. It takes us 600 watts of electrical power to do that. 100 watts of transmitted power takes us 300 watts of electrical power. This TS990 from Kenwood, yes, I like Kenwood. The TS990 is a really nice HF base station system. It actually has a built-in power supply, so it has an AC input. And you see this AC 120 volts and a power consumption of 720 VA. What the heck are VA? I'm going to call them watts for now, and we'll talk about that in just a second. So it wants a 720 VA at maximum power transmit and 120 VA at receive. So what's the difference between VA or volt amps and watts? Well, it's actually kind of interesting. Watts refer to the real power. Volt amps refer to the apparent power. Now, when you're working with DC, your DC circuit is a pure resistance circuit. With the conductors being the only limiting factor, but the impedance of the conductors being the only limiting factor. So watts are a good measure of the real power. If you have 320 volt devices that want to work at 200 watts, 400 watts, and 600 watts, you can just add them up to know how much power the circuit requires, 1200 watts. AC also has inductive resistance because remember in an AC circuit, the power is going up and down all the time, right? So as the power goes up and down, the electrons are accelerating and decelerating in the circuitry, and that causes some inductive resistance as well. So typically, when you add those up and you get 1200 volt amps, it's not necessarily 1200 watts, but it's usually close enough in our calculations that we're going to be doing. So you should keep in mind that if it's measured in volt amps, if it's working with AC, you should be a little bit leery of using that number as watts, but you're probably okay. You might want to pad it a little bit just for safety's sake. So what if I can't find the volts, amps, watts, or whatever? Well, you can measure the actual usage of the device. For an AC device, there's a little gadget you can get called the kilowatt. It plugs into the wall, and then you plug your device into the kilowatt, and it will record and show you how much power it is using at any given time. So you plug it in, turn it on, let it run, let it do its thing at its highest power level, and you can read how much power it's using directly off the screen. For a DC circuit, you need something like a DC electricity monitor. This is something that has to sit in line with the load, right? Because DC, you can't just like tap off it and measure directly what the current is. You have to be in line to measure the current. So this device will plug in, it'll measure your voltage and your current, calculate your power, and how much energy is being used. We'll talk about the difference between power and energy in a minute. But this is something that you can get for less than $20 on Amazon. If you have a multimeter, you can use your multimeter to figure out how much power your device is using. Again, plug it in, set it up for voltage, measure the voltage across the power that's being consumed, and then put it in line, set it for amperage, put it in line with your circuit, and measure the current that's actually being used. Multiply those together and you'll get your watts.
Can I have a comment on that?
Yes, please.
Just be forewarned, those are typically less than 10 amps because these aren't really amp meters, although they can be used, but they're not made for anything greater than 10 amps.
Yeah, you don't want to put it in line with your 50 amp load with a little multimeter like that. You definitely want to have some kind of a DC power device that is designed for that level of power. Your other option is to look it up. You can look in the manual like I did with the Kenwood radios, or you can Google it. Sometimes you can find something good online that has the actual information that you want. So let's talk about the difference between power and energy. We've talked about how much power we need in watts, right? So that's how much instantaneous power we want at a given moment, right? If we have everything going at once, we can sum up all of our watts, all of our power from all of our devices and say, I could need up to this many watts at a given moment if I'm doing everything all at once. Obviously, I'm not normally going to be doing that. I'm probably going to be listening more than I'm talking on the radio. I probably won't have my lights turned on if it's daytime. I probably won't have my microwave running unless I'm actually heating up some food. My oxygen concentrator I'll probably have running all the time. But I want to know not just the power, but I want to know the energy that I need to have, right? So energy is power usage over time, and it's measured in joules. Now, you're going to sit here and say, joules? What the heck are joules? We never talked about joules in high school, right? We talked about watts, and we talk about what power unit do we use for energy typically? Do you guys know? Any guesses? No guesses. All right. We typically talk about watt hours, or typically kilowatt hours if we're talking about like how much power our house is using or something like that. So how do we get watt hours or kilowatt hours from our energy or our power that we're using? Well, just for completeness, 1 kilowatt hour is about 3.6 megajoules, or 3.6 million joules. So that's one of the reasons why we don't use joules, because they're not a convenient unit to use. How do you calculate watt hours? Multiply watts times the hours that you want to be running your device, right? So if your lamp takes 60 watts of power and you want to run it for 1 hour, it's going to take 60 watt hours of energy to do that. If you want to run it for 2 hours, it's going to take 120 watt hours of energy, right? So that's how you calculate that. So what's next? Well, we know how many watts we expect to use. We have some idea how many hours we need to run our stuff. How do we store the power to use it later? Obviously, we're not going to be able to plug into the wall, right? If it's an emergency situation, the power is out. So what are we going to do? We're going to use batteries. So let's talk about batteries. So typically, your batteries have an energy output capability measured in watts. They're going to have some kind of voltage that they're able to put out, and that voltage, and they'll have some kind of a current maximum that they can put out. And so you can calculate how many watts your battery can put out at a given moment instantaneously. They'll also have an energy density measured in watt hours, which will tell you how much energy is in the battery. Sometimes you'll see that recorded as amp hours. In that case, just multiplied by the voltage, and you'll have your watt hours. So let's talk about different types of batteries. So we have alkaline batteries, we have zinc carbon batteries, we have dry cells, lead acid batteries, nickel cadmium batteries, nickel metal hydride batteries, and lithium ion batteries. I'm going to talk about each of those. So alkaline, zinc carbon, and dry cells, these are not rechargeable. Why would we want to use them? They're cheap, they're readily available. You can walk into any Walmart anywhere and buy a pack of AAA cells or AA cells for a few bucks and have a whole stack of them. They last for a long time. You could have a battery that sits on the shelf for 10 years, grab it off the shelf, shove it in your device, and it's still going to work fairly well. It's still going to have a lot of power left. They have different sizes for different needs. So if you've got a heavy-duty flashlight that wants D cells, you can have those. If you've got a smaller device that takes AA's or AAA's, you can buy those as well, and you have to have more power than you need. There's also 9-volt and 6-volt batteries. Who remembers the 6-volt batteries that were typically used in the big spotlight lanterns that people used to have all the time? You'd have it and hold it with a handle, and the battery would sit underneath the handle, and there's a big light on the front.
Yeah, they still sell them.
They still sell them because people still use them. So,
yep.
And they're not bad. They last a long time. They hold a lot of energy. They only put out about 6 volts as a power level, but they'll hold a lot of energy and they last. So typically, if you've got a handheld radio, you can buy a little adapter that plugs in where the power pack would that will take either AA's or AAA's on the radio. I've got my Kenwood F6. I have a battery pack for that takes 4 AA's. It can only operate the radio on low power, so 1.5 watts, but and typically only for a few hours. But if I'm in a situation where I don't have any other way to charge my radio and I need to use it, I can plug that in. I can grab a pack of batteries off the shelf, or I have some in storage. I can grab some in there, throw them in there, and I can have my radio up and running. My B72 has a pack that holds 6 AAA's, so smaller batteries, but more of them. They also have the same limitations. They can only run on low power with that setup, and it doesn't last for a long time, but it does work. So it's something to consider. Always have some batteries on hand. I recommend having alkaline batteries. The technology for alkaline is better for electronics. The zinc carbon and dry cell types, I don't think you ever really see the dry cell types anymore. They used to have a size B battery that was a dry cell, and it used a technology that you don't see it too much anymore. But the zinc carbon batteries you can still find. Those are pretty good in a flashlight. They're not so good for running electronics because their power tends to fade off gradually over time, whereas an alkaline battery will keep its output level steady for a while until it gets close to the end of its life, and then it'll drop off suddenly. So that's usually better for electronics. So pick up a stack of alkaline batteries and just keep them on hand. You'll never know when you need them. You want to have them when you need them, so that you don't have to run to the store and try to scrounge them up. Lead acid batteries, there are several different types. Your typical car battery, your sealed lead acid battery. Why would we not want to use this for powering a radio? Anybody have any ideas?
Well, they're
Go ahead, Dan.
they're made for high amperage for a very short period of time. They're not made to constantly use the power out of them.
Exactly, right? They're designed to start your car, and starting your car takes a high draw of amps, but only for a few moments while it cranks the engine, right? So they're great for starting your car, but they're not so great for running a load that is going to be a fairly constant load for a long period of time. Even though they got plenty of power in there, the way that they get that power out isn't the greatest for that kind of an application. But they do have a type of lead acid battery called a deep cycle battery. And you'll see those typically in marine applications. You'll see them in RVs. They're a little bit more expensive than your typical car battery, but they have the ability to run at a set power level for a long period of time, and they have a very gradual decline in their capability, right? So they're a good battery to use for powering this type of equipment. Plus, they also handle being discharged quite a ways and then recharged. They handle that a lot better than the typical car battery. The car battery wants to stay fairly well charged all the time, right? Normally when your car is running, your alternator is providing power and keeping the battery topped up. It's only when your car is turned off that the battery is needed. And so the amount of time that it wants to be running is much lower. The deep cycle battery is actually designed to handle that usage pattern where it's running for a long period of time and drawing the battery level down quite a ways. You'll also see these AGM cells. These are typically what would be called a no maintenance battery. You can't add any water to them or anything like that. Hang on one second. No. So the advantage of these is that they generally don't spill if they fall over or something like that. There's no liquid acid in them that's going to get all over your stuff if it happens to have a problem like that. Gel cells are similar. They use a chemical that is in a gel form as opposed to the liquid reactant inside the battery. So those are typically good for applications that we're talking about here, where the battery might get jostled, it might get tipped sideways or something like that. They typically work well for that. Lead acid batteries have good power density. They have good temperature tolerance. They can handle cold temperatures. They can handle high temperatures. They can be charged and discharged a lot of times if you're using the deep cycle batteries. The drawback for them is they're heavy. They're not super expensive compared to some of the other technologies, but they are quite heavy. So if you had a couple of different batteries, one was a lithium ion and one was a lead acid. The lead acid would probably weigh about 5 times as much as the lithium ion. So NiCads or nickel cadmiums, these used to be really popular in the 70s and 80s, early 80s. They have a good life cycle. They can be discharged and charged about 2,000 times before they will wear out. They maintain their power level pretty well. They have pretty decent voltage. Your typical AA alkaline battery is going to put out 1.5 volts. A NiCad will put out about 1.3 volts. So,
Hey, Sherwood,
Yeah.
could you mute, please?
Did I mute?
Please mute.
yeah, you're honking at
Where
it.
do I have the mute button on my cell phone?
I got it here. You're muted now, Sherwood. So yeah, the nickel cadmium batteries. The name NiCad is actually a trademark name for a specific brand of battery, but I think pretty much like Xerox and Kleenex, pretty much everybody calls these NiCad batteries, regardless of who makes them. But they have pretty good temperature tolerance. They do have this thing called a memory effect, which what this means is if you don't let the battery discharge very far and then you charge it back up again, then after a while of doing that, the battery decides that that's as far as it's going to let you discharge. And so when you discharge it that far, then it doesn't want to provide any more power after that. That can be overcome with battery cycling equipment, but it's a definite drawback of the nickel cadmium type batteries. They lose about 10% of their stored power per month. So if you leave a box of these sitting on the shelf for a year and then go grab one, it's not going to have any power left in it. So you need to use them, maintain them, charge them, and keep track of how they're being used. They actually have chargers that will take the battery and discharge it all the way before they charge it up again to avoid this memory effect. But they're specialized nickel cadmium rechargers that'll do that. Don't see these around too much anymore. They are still available. There's still equipment that uses them. I know Ragnar has a Kenwood T THD7 that uses NiCad battery packs. And so he can probably tell us about how that memory effect affects things and how those batteries fail over time. Let's see.
I can add something right now, if you don't mind.
Yeah, please do.
I've gone through 2 of those battery packs, and now on my D7, I just have a pack that I put regular batteries in, and it works fine because they, just regular batteries, and so the battery pack that came with it, I thought it was not a good choice. So anyway.
Yeah, unfortunately, that's what was available back in those days, and so that's what manufacturers used. Those were pretty much replaced with nickel metal hydride type batteries during the 80s and 90s. These batteries are great because they'll hold about 2 to 3 times the energy of the NiCad. They actually only lose about 3% per month, so they'll actually hold on to their energy pretty well. They only put out about 1.2 volts per cell, which is a little bit less than the NiCads, but you can work around that. And we'll talk about ways to work around that in a little bit. They do have a pretty similar life cycle where you can charge and discharge them up to about 2,000 times. They handle temperatures pretty well. They don't handle low temps as well as high temps, but they're still pretty decent. Pretty much replace NiCads in most applications. One thing you have to be careful of with nickel metal hydride is if you discharge them too far, it can physically damage the cells and make them unusable. Also, if you have a battery composed of multiple nickel metal hydride cells, a single cell can fail in such a way that it destroys the entire pack and kills all the rest of the cells in the battery. So that's something to be aware of. The cells also have an internal fuse that can fail on a high voltage, like if you're trying to charge it, but you're using too much power to charge it, or a high temperature condition, and it can actually permanently destroy the cell. So those are things to think about with the nickel metal hydride. You have to use a charger that is rated for nickel metal hydride charging so that it doesn't overheat or overpower the cells as it charges them. And then you shouldn't have too much trouble with those. But they're pretty good technology for batteries. The king of the block right now is lithium ion. You typically find these in batteries where multiple cells are enclosed in it. So if you look at this picture, this battery pack here, there's probably 12 cells in there, I would say. You typically won't deal with a single lithium cell like you would with an alkaline cell or a NiCad or a nickel metal hydride cell. There are a few different technologies available. Lithium ion is one of the earlier ones. A lot of laptop power supplies or power packs, battery packs are lithium ion. You'll also find lithium phosphate, and the new kid on the block is the lithium iron phosphate or LiFePO batteries. And they have some really cool characteristics. They have excellent cycle life. They can handle deep discharge. They're very lightweight. You do have to have a charger that is aware of the type of battery that you're going to be charging, particularly for the LiFePO batteries. They need a very particular charger for those, and they're not cheap. They're fairly expensive batteries. So those are all considerations for batteries that we need to take into account. What about our AC devices? We can use an inverter. An inverter will convert DC to AC. There are 2 different types of inverter, ones that put out a square wave, as you can see here, and ones that put out a sine wave, as you see here. The square wave inverters are cheap. They are fairly efficient as far as power loss. They don't lose a lot of power. They're really noisy. Radio equipment probably doesn't like them because they're really noisy in their operation. And I don't mean like ambient noise, well, ambient noise as well, but not just ambient noise, also electrical noise. So they will, because of the way they switch the energy back and forth, they're typically a lot noisier than a sine wave inverter. And some equipment doesn't like the square waves, typically motors and devices with switching power supplies like computers. And we'll talk about that in a second here. Another option is that you can actually feed DC power to your AC to DC converting power supply. And this is something that confuses a lot of people. They think, how in the world does this work? And I'll actually talk about that right now. So
Before you go on,
yeah,
one comment on the inverters.
yeah,
There's also kind of, and you may get into this, a hybrid between the
yeah. There is a hybrid. I don't have that on the presentation, but I did read about those, and they are in existence. So if you want to tell us about that, Dan, please do.
Sure, it's called a modified sine wave inverter. Again, a lot less expensive than a pure sine wave inverter. And you take that square wave that you see on the right-hand side there, and you make little right angle steps so that it kind of, at a distance, looks like a sine wave. But when you are, he's doing the exact same thing right there. He's stepping up and down up there. Most equipment that, like your power supplies, your computers, your refrigerators, things that like the sine wave, they don't do a very good job handling the modified sine wave. So it's good if you're just using it for some applications, but for your computers and things, electronics that are sensitive to the sine wave, not the best thing for you. So there's a reason why the pure sine wave inverters are the most expensive type, because they actually send out a true sine wave on the line.
Thank you, Dan. So as far as our DC fed power supplies, if you think about what happens inside a power supply, so I'm talking about like your typical wall wart, or if you were to look inside that, your TV where the AC power comes in, the first thing that it's going to hit is a rectifier bridge. And a rectifier basically is going to take the AC current that's on these two legs, and it's going to hand you off a fairly steady DC current. Typically, there will be a capacitor involved in here as well to keep that thing balanced, but it's not shown on this diagram. But as long as you've got this rectifier happening first, it doesn't really care if the power is coming in on both sides. If it only comes in on one side, like a DC power feed, it just comes in and goes, goes straight through the rectifier and out the other side. And same thing with the other side. If it's coming in on this leg, it comes in here and goes straight through this diode and out the other side. So if you're feeding DC power to a rectifier, you can get DC power off the back of it. You don't have to feed AC power to it. Now, some devices don't work with that. For example, this is an example of the wall wart that came with my D72 radio, and it actually will work with this. So the power comes in, there's a rectifier, and it immediately hands it off to some switching circuitry, which handles the voltage conversion and everything and hands the power out this way. My power supply that came with my F6A, on the other hand, which weighs about 8 times as much as this one, it actually, when the power comes in, the first thing it hits is a transformer, which steps the voltage down to the voltage that it wants to put out on the other side. If you got a power supply like that, it's not going to work with DC on the input, because transformers don't like DC. They only really work with AC. Excuse me. So that's something to consider. Best thing to do is experiment with your power supply. Some of them care which side has the power on it. Some of them don't. Some require a minimum voltage to work. Most of those power supplies are rated to go from like 100 volts to 240 volts. Some of them will go down as low as like 70 volts on input and still work just fine, still produce the right power on the other side. So you'll have to do some experimentation. Do that before the emergency happens. So be thinking about that now. A good way to test this kind of thing is with a bench power supply that puts out a set DC voltage and power level that you can control. So you can set it for a particular voltage and feed that into it and see what happens, right? So that's something to think about doing now before the emergency happens. What if your power isn't clean? For example, your batteries might be putting out 14 volts when they're fully charged. They might drop down to 8 volts or 6 volts when they're low. You know, this could be a problem if your equipment is expecting 13.8 volts exactly, right? Most amateur equipment wants 13.8 volts. Most of it is pretty tolerant, plus or minus 15%. But again, that 15% only takes you so far. Most devices, apparently my image covered up part of my texture. Most devices intended for automotive use want about 12 volts. They expect to take up to 13.8 because that's typically what your alternator will put out. That's the amount of power that you'll be using to charge your lead acid battery. But they'll take 12 volts. They'll take less. But they like something around that 12 volt range. Some equipment you're going to find wants 24 volts. I know that, for example, we've talked about Airden, the amateur radio emergency data network before, and we've talked about the devices that you use for that. They're little Wi-Fi access points, essentially. They typically want 24 volts. So that's something to consider, is that your equipment that you want to power may want more than 12 volts. It may want 24 volts. Some equipment wants 48 volts. For example, a lot of the IP telephones that you will find are very happy to have 48 volts, and they don't want less than that. So you need to keep that under consideration as well. Pay attention to what your equipment wants and what you need to supply to it. But basically, you can use a voltage regulator, very simple circuit, to produce power at the voltage that you want. So input comes in at a variable level. Maybe it goes up, maybe it goes down. The current coming out of it is very solid and steady at whatever your device is set to do. So there's a particular chip that does this, LM340, and there are different variants of it for the different output voltages. Excuse me. And so you want to incorporate some kind of a circuit like that in your emergency power setup, so that you're sure that you're getting power out that is consistent with what your devices want. We'll talk a little bit more about where this voltage variance can come from too, as we talk about solar in a minute here.
So are you going to talk about the various voltage inputs for inverters?
No, I was not.
Okay.
My coverage of inverters is complete at this point. So if you want to add something to the inverter.
Let me just add real quick. Talking
Certainly.
about solar systems and putting inverters in there, most people, and the most common type of inverter is taking 12 volts input and having it come out at 120 volts. The higher voltage inverters that you can get are actually more efficient. So if you can get a 24 volt, if you can set your battery bank up to use 24 volts into your inverter, a much more efficient design than a 12 volt bank of batteries. They also have 36 volt inverters and 48 volt inverters. There's also 72 volt inverters. There's all kinds of inverters like that. And the higher voltage means more efficiency when it puts it up to 120 volt DC. That's all I have to say about that.
Okay, yeah. So in general, higher voltages are more efficient. They require less current for the same amount of power delivery. And so your wires can be thinner and all of that. So that's all things to consider. So let's talk about our batteries. How many batteries do we need? So you've got to calculate your energy requirements, your watt hours that you're going to need. You calculate your battery's energy capacity. It's typically going to be in amp hours. So you're going to multiply it out to a particular voltage that the battery is putting out to get your watt hours. Keep in mind how deeply you want to discharge your battery. Do you want to run it all the way down to nothing? Do you want to stop at 50%? So keep that into account. If you've got a 7,000 milliamp hour battery, that's a 7 amp hour battery. And if you're going to draw it down to 3.5 amps, that's 50%. You may find that your life of your battery gets much less if you go lower than that. So those are things to consider when you're designing your system. How can we recharge our battery? There are several different options. We've got, I call it mains power. That's basically plugging it into the wall. That's great when the power is there. It's not so great when the power is out. There's also solar generators, wind and water generation systems, and I'm going to talk about those in a moment here. So I put mains power on here because if you have a setup where your battery has enough power to last you for your entire length of time that you expect to be without power, then you have no reason to charge it while you're using it. It'll work just fine. So if you're planning like a field day outfit or something like that, where you want to have your radio operate for 24 hours and you've calculated how many batteries you need to bring with you to satisfy your power requirements for 24 hours, you don't need a charger. Excuse me. So those are things to keep in mind. You can charge your batteries up before you go and then use them while you're there and then recharge them when you get home. So let's talk about solar power. So a lot of people are putting solar power panels on their houses nowadays. There are companies that come out and they'll say, how much power do you use? Well, we can make your power bill go away, you know, and all of these things. And those are what they call grid tie systems. And those are great when the power grid is working. Those are absolutely fabulous. They'll bring your power bill down to almost nothing. It's essentially free power, right? So power of the sun, you're essentially charging back the power company for energy that you're putting into the grid during the day when you're not using it, and then you're using from the grid at night and paying for that power. So your meter will actually run backwards during the day when you're putting power in, more power than you're using, and then it'll run forwards at night when your solar power panels are not generating any energy and you're using power from the grid. Those are fabulous for energy efficiency. They are fabulous for ecology. They're fabulous for, you know, all these different things. They suck for emergency situations where the grid has gone away, because a lot of times those panels won't do anything for you. In fact, they'll shut off if the grid is not connected. And they do that for safety, right? If your grid goes down, say your power line coming into your house falls on the ground, a tree knocks it down or something, you don't want the house side of that wire to have power coming from your solar panels when the power company guy comes to fix it, because he's going to assume that there's no power on that side and he's going to pick it up and get a nasty zap. So those systems will automatically stop feeding power into the wires and stop producing power if the grid goes away. So they're great for that power saving, that energy saving, energy conservation, saving you money. They're not great for emergency power situations. Solar panels will produce DC power. They'll produce it at a particular voltage and a particular amperage rating, typically. You know, your panel, when you buy a panel, it'll tell you how many volts it expects to put out, how many amps it expects to put out. You can calculate your wattage that's coming off of that. You definitely want a charge controller unless you're just using lead acid batteries. Lead acid batteries, you can basically just lay whatever power you're getting from your panels directly on them and it will charge them just fine. But if you're using anything like lithium ion batteries or anything like that, you definitely want a charge controller. And it's not a bad idea to have a charge controller even with lead acid batteries, because then you can vary the rate that you charge the battery and you can top it off and trickle charge it when it's full and that kind of thing. The charge controller will handle all of that for you. So you probably want a charge controller no matter what. Things that you have to consider is, where am I going to put my panels? How much sun am I going to get? How much power am I going to get from them? The power is going to vary during the day as the sun moves over. If it's a cloudy day, you don't get much power. If it's nighttime, you don't get any power. Some of these panels will actually use energy if they're not generating energy. So at night, they might have a parasitic load of 1 to 3 amps or something like that per panel. So you need something that disconnects those panels from your batteries when they're not actually giving you power. Again, that's what your charge controller is going to do for you. Jeez. I got to quit clicking when I'm trying to highlight something. So solar panels are great. They provide a great resource that's, free energy from the sun, but you do have to pay attention to factors like how do I get that energy into my batteries? How much energy are my panels producing? Are they producing enough during the day to charge my batteries up so that I have enough power in the batteries to run everything I want to all night long when the panels are not producing any power? So those are all things to consider with solar power.
And one more thing.
Go ahead, Dan.
One more thing is if you have multiple panels, some systems, if you have shade on one panel, it affects the entire array. And so typically, if you have a grid tied system where you have microinverters under each panel, if you have one panel that is shaded, it won't affect the other panels. But if you have them all tied together, coming into a common inverter, shading 25% of one panel, it's as if you're shading 25% of all the panels. And so you got to be careful on how you set this stuff up and how the panels and well, if it's a microinverter, how the microinverters are set up for that.
Yeah, so site planning is very important with your solar power. Now, if you've got a portable solar panel and you're taking it out camping and you're just going to set it up out in the field or something, you can position it somewhere where the sun's going to be shining on it. You only care that it's getting sun while it's connected to your batteries and charging them up. So, that's a totally different animal from if you're putting solar panels on your house with the intention of using them for emergency power. And there are grid tie charge controller systems that support batteries as well and will actually power your house from the batteries if the grid goes away. Those are significantly more expensive to get into, and they're not really common, but those are available. If you ever talk to Bob Berninga, he is WB4 APR. He's the guy who created APRS, and he's a faculty member out at the U.S. Naval Academy in Annapolis, Maryland. He is a big proponent of solar power, and he says grid tie is the way to go. Batteries are terrible. Don't do that, and you'll save a lot of money. But also, he understands that that's not for emergency use. For an emergency situation, you still have to have your batteries and all of that set up. So those are all things to consider with solar power. So let's talk a little bit about generators. There are several different types of generator. You can have a permanent installation generator. We've all seen these like on the side of the hospital or on the side of a doctor's office or something like that, where they need reliable power even if the grid goes down. These are typically a permanent installation. They're expensive. They can often run on multiple fuels, so they can be either diesel powered or natural gas powered or run off of a propane setup, something like that. It'll power your whole house. It's a great gadget. These are great if you can afford it, and if you don't mind the noise of the generator running, and you can maintain it and do all of the appropriate testing and operation of it. Typically, you'd want to have a contract with some company that would handle maintaining and testing it. But if you have the resources and the need, you can definitely set up one of these permanent power generators outside your house, and it will happily run your whole house for you. The natural gas ones are great because even if the power goes out, typically the natural gas is continuing to flow, and then you don't have to ever worry about fuel. Gasoline is a problem because gasoline will tend to degrade over time, but diesel generally doesn't do that. Diesel sometimes has issues in very cold environments, so that's something to consider. Your diesel fuel can actually gel up if it gets really cold. So if you're putting this at your cabin up in the mountains, you want to be aware of that factor. Propane is generally a pretty good fuel for that type of a setup. You can also get a trailer mounted generator, and this one here is also typically a commercial setup. These are very big generators, very powerful. They're very expensive. They're usually gasoline or diesel powered. this would be great for running, for example, an EOC type of setup or a portable EOC type of setup where you have to set this up in an emergency situation. You pull this generator out of the shop, set it up, and run all of your gear off of it for whatever length of time you need to. Again, they're usually really expensive. These portable generators are usually pretty handy. These typically run anywhere up to $700 to $1,000. You can get them at Costco. They'll typically put out enough power to run, your fridge, your stove, your microwave, your furnace, and your radios, of course. You've got to be careful that the inverter that's included in this setup isn't a square wave inverter. Sometimes on the cheaper units, they are square wave inverters. And we talked about those and the problems of those earlier. They do have a limited fuel supply. You can see on this one, this orange part is the fuel tank. It's mounted right on top, so it's easy to refill. But you generally are going to want to turn this thing off before you put gas in it because you don't want to be playing with liquid gas while this thing is running. So those are things to consider. There are also the small portable units, which are luggable. Basically, these are small enough that you can carry it with you. They typically will run for an hour to two on a tank of fuel. You definitely have to turn it off to put more fuel in because the fuel tank is inside this unit. They're good for charging of your batteries periodically. So if you have a situation where you have sufficient batteries to run for several hours, but you want to make sure that you can recharge them, you could set up something like this and it would provide you with enough power to recharge those batteries in a fairly short period of time. So generators are great. Problems with generators, they use fuel, which you have to manage, and they require maintenance. If you're going to be using a generator for something like field day, you're probably going to want to check it out before field day, like a week before. Make sure that the filter's clean, make sure that the oil has been changed, make sure that the fuel is good, make sure that it runs and that it produces power appropriately. When I was a teenager, we rented a motorhome from a friend of my dad's for a couple of weeks. We went and traveled around and went through Yellowstone and some other different places and checked things out. And the motorhome had a generator on it, but this generator had a problem where it hadn't been run for a long time. And so it had a lot of carbon buildup on the carburetor. And so whenever we would put it under load, it would rev up and then slow down, and then rev up and then slow down, and then rev up and then slow down continuously, like, on a cycle of probably 10 seconds, up and down, all the time that it was running, that it was under load. And it was very, very annoying to everybody around us. And so we ended up not using it and finding campgrounds where we could actually plug into shore power. But, that's something that if we had known about that and checked it out before we went on the trip, we probably could have had that fixed before we left, and then we would have been fine. So definitely, if you're using a generator or something like this, you want to test it out, make sure that it's going to work, make sure that it's not going to have any problems. Check it periodically.
Comment?
Yes.
Could you go back to another screen there? Okay, so a couple of things about this. Just a quick plug for Harbor Freight. They have a 3500. Actually, it's a inverter type of generator, which is the next picture. This one, the picture that is shown, is kind of like a 2,000 watt inverter. Yeah, I can see IQ 2000. Some of them are extremely efficient, running the 3,500 watt inverter generator from Harbor Freight. With a single tank, we were getting about 8 hours on it.
On one of these little ones like this?
No, on a 3,500.
On one of these?
No. It's just a larger inverter type.
Okay.
Okay, and I have a 9,000 watt generator, very noisy, but it has a 50 amp connection on it, so I can charge, or I can plug in any RV, any fifth wheel, any large RV with multiple ACs and refrigerators and that kind of stuff. It's also made for my house if I want to hook it up that way. But these inverter type of generators, which is the next picture, there's a lot of them that you can parallel connect them together. So you can hook up two 2,000 watt generators so that you can run uh, like your ACs on your RV or something larger that requires more than 2,000 watts. And so that's, this technology has come a long way. These inverter type generators, some of them have a automatic low power, or you can manually set it for low power, which means that if you're only pulling 500 watts, there's no reason to have this generator run full throttle. You can half throttle it down and still maintain whatever it is that you're trying to drive, and extend your fuel by a humongous amount. Ryan, he had that 3500 inverter type generator, and he was actually telling me that on the low setting, just powering off his HF equipment, he was getting at least 12 hours on a tank of gas, usually 15 hours when he was doing a 24-hour stint. So you can play with them, and if you control what you're asking the generator to do, you can really extend the life of having to refuel it and that kind of stuff. Plus, with these smaller ones, you have the ability to hook multiple smaller ones together to make it a larger one. So they've come a long way, baby, to coin a phrase.
So yeah, you definitely want to check out the different technologies that are available. And again, experimentation before you need it is a good thing to do. Make sure that it will actually run all the things that you want it to run. So let's see, other alternate solutions. There's wind power. Basically, it's free power. I put a little trademark here, free power, yay. These are not cheap. They are $500 to $2,000 for one of these units. You can mount this on a pole. You can attach it to your trailer. You can mount it permanently onto your house or something like that. They'll basically give you free power as long as the wind's blowing. Problem is, the wind doesn't always blow. There are going to be times when this is not going to produce any power at all. It's very site dependent. It does work at night, unlike solar power, but the power can vary wildly. So you definitely want to feed this power into some type of a battery bank and have your voltage regulators and things so that you're making sure that the power that you're getting out is not the same as the power that you're putting in from this type of unit. But these are readily available now. This is one particular design. I've seen some other designs that have it looks kind of like a barrel where the vanes are vertical and they spin around in looks like a cylinder. Those are kind of cool. But these things are actually pretty effective. They work fairly well. You can go with some kind of a water power solution. Problems with this are you need a good supply of water. You need a good height differential. You need to have some way to bring that water to the power generating apparatus. These are not cheap. They're like 20 grand to put one of these systems in. But if you've got a piece of property where you have a pond or a stream or something like that, and you've got the appropriate slope and you can take advantage of your site, you can actually get totally free power 24/7 off of one of these units. And it's just like the Cadillac of the free power setup. There can be some ecological issues if you've got to dam your stream up. That can cause problems for the fish that might live in it. But in general, you can design your site appropriately. This one you can see here is a turbine system. It's drawing off of like a canal or an irrigation canal, and so it's got this basically door that can close off or open the spillway. The cover is off of this. Normally there would be a cover over the top of this, but you can see the water comes in and it circles around here, and there's a turbine underneath here that gets spun by that water, and the water comes out down here a couple of feet lower. But it's really efficient. It's good at producing a lot of power. It's not really portable. It's not something that you want to use in an emergency situation. It'd be more of a like a remote setup where you don't have utility power, but if you have the site for it, these are great. Water power is probably one of the best utilizations of alternate power that are out there. Another option is the hand crank generator or bicycle powered generator. I saw this on Amazon for $40. It produces about 20 watts of power. I can just imagine sitting there and cranking that thing for 6 hours trying to charge my my 12-volt car battery or something like that. That would not be a fun way to spend 6 hours, but it would get the job done. I would think it would be very tiring to run it for any length of time. Probably something like this would be great for charging your cell phone or an HT. I don't think I'd use it for much else than that. These bicycle power generators you can get, they're about $200. They can produce about 200 watts of power. They're good exercise. I don't know if you guys have ever seen the show Red Dwarf, but there was an episode one time where the two characters, Lister and the cat, were stuck in the ship with all the power out, and Lister was getting ready to go to bed, and Cat said, my turn on the electric blanket, pedal. And so Lister had to get on the bike and pedal to produce electricity to run Cat's electric blanket. So that's something to consider. You could use something like this in an emergency. It would allow you to generate power if you needed to. Not really the best solution because it is going to be really tiring. Other alternatives are geothermal power. Again, that's going to require quite a bit of site setup. These are mostly for larger installations, not your typical home solution. Definitely not portable. Wave or tidal power. Nuclear power. Nuclear power is fabulous. Have you guys ever heard of an RTG? It's a radiothermal generator. This is the type of power generator that the Voyager space probes are using. Those guys took off in the 70s, and they are still running today, 50 years later, and they probably still got 50 years of power left in them from their radio thermal generators. You're not going to put one of these on your house. You're not going to get licensed for this in your home environment. So, and it's definitely not going to be something you're going to want to put in your trailer and haul with you. Unlike the guy on The Martian, where he dug one up and used it to keep him warm while he was traveling from one base to the other.
It could happen.
It's very unlikely that you will have one of these. Let's put it that way. But they are some alternate solutions that are out there for power that a power company could install something like that. A small town or a small commune or something like that could put in some kind of a geothermal power setup or something like that. It's probably not something you're going to be running yourself. So that's about the end of my presentation. So if there's any questions or any comments, I'd be happy to entertain them at this time. I have some links on here. This is where I got some of my information from. The ARRL has a lot of good information on power if you're a member. I'm not a member of the ARRL, so I don't have access to the back issues of QST magazine, unfortunately. But there is a lot of good information on their site. Then, if you Google for emergency power, you can find all kinds of good information. And if you're setting up, like Dan, you're setting up your property out there, hauling power lines to your place is probably going to be prohibitively expensive, like to the tune of $100,000 plus. So you may want to look into some kind of an alternate power solution for running out there, so you don't have to depend on your generators all the time. But I would recommend solar, wind, water power if you can get it, if you've got that kind of resource on your land. So those are things that you can consider for your emergency power use. And that's all I have. So questions, comments?
I do have one comment on the bicycle pedal generator.
Yeah.
I'm looking at Amazon right now, and they are $200, but
It
they're
says
only
it'll only do 20 watts. There's no way that thing is only going to do 20 watts. If
you,
you look at something like that for real, you're going to get way more than 20 watts out of it. So I looked at that and I said, well, that's just not a reasonable amount of wattage to get out of something like that. Now, I think they're talking about 20 watts at 240 volts, because if you look at it looks like it has an integrated inverter on it,
yeah,
and that definitely looks like a European power outlet that they've got there,
yep.
multi-type power outlet. So it's probably 240 volts. So, you're if you're talking about running DC, something DC off of that, you're definitely going to get more than 20 watts out of it, I think. So I would take that with a grain of salt when you look at that.
Okay, very interesting.
I did also find a 300 watt generator with a pulley on it that you could attach to your bicycle. That is significantly smaller than that.
Yeah, the
So,
e-spin bicycle generator is
so
another one.
yeah, so there are other options out there. So, it's definitely something you would want to investigate if you are interested in that sort of thing. I've also seen a setup that a guy built where he actually built a large, uh, almost like uh, a hamster wheel, but human-sized, in his off-grid cabin, and it's all made out of wood, and it's really cool. And he can get in that and walk and generate power for his cabin. So it's certainly something that you could consider, but again, unless you've got some serfs or children that you could put in there and make them walk, it's probably not going to be the best solution for you guys.
I have, if anybody would like, plans to build a bicycle generator using an alternator. Um, so alternators are something that is, if you can get the alternator to spin, it generates electricity. In particular, 14 volts. So if you want that, I just email me and I'll send it to you.
Yeah, send it to me and I'll put it on the website with this presentation.
Okay.
I had one question on okay, most of us are doing like little deployments in our vehicles, or deployments where we'll set up on a table or something and we're gone for a few hours. Maybe we might need like a mobile radio to work that. What would you suggest as the best battery or something to get to where we could do that?
So one thing you could do is run off of your vehicle's battery. And if you're going to do that, you're going to want to get a device that will monitor the battery level and will cut it off when it starts to get low, so that you don't discharge your battery so much that you can't actually start your engine. Your better choice would be to get a deep cycle battery, like a deep cycle lead acid battery. If you're running out of a car or a truck or something like that, the weight is not really going to bother you that much. And you can wire that in. A lot of trucks will be configured such that you can wire in a secondary battery. I've even seen them that have dual alternators on them to charge the batteries faster and things like that. That's obviously not something you're going to want to invest in if you're not doing it a lot. But getting a deep cycle 12-volt battery and hooking that into your car's power system, just tie it into the regular system, but use one of those. I think it's called a battery isolator circuit, something like that, so that power can go from the engine into your battery when the engine is running, but it's not going to draw from the vehicle's battery when the engine's not running, right? So you don't want to draw down your vehicle's battery unnecessarily to the point where you can't start the car anymore. So those are things to consider for that type of a setup. And you might want to do that regardless if you're running your radio in your mobile and you don't want to necessarily have the engine running all the time. Adding a second battery to your vehicle is certainly not something it's certainly something to think about, and definitely worth doing. So if you happen to have a hybrid vehicle or an electric vehicle, then you typically have significantly more power available than you would need. So, those are good choices for that kind of a setup as well. Other questions?
Just another comment, looking at notes fieldday.pdf, that kind of got me thinking, when you're dealing with generators on field day, you got to make sure that you get the right generator so you're not putting line in the noise. That is the killer of RF. When we're transmitting HF and you're using a dirty generator, all kinds of noise
Right.
that you can hear. So you gotta use the right generator,
A
especially
lot of that
for
noise,
comms.
a lot of that noise will come off of the inverter as well. So that's something to
Yeah.
make sure that your inverter is shielded or is fairly clean. One of the interesting factors that I found when I was looking into that field day stuff was if you're running your field day setup off of batteries, it is allowed to take those batteries and hook them up to a generator and charge them during field day. So if you have like 2 sets of batteries, you can have some batteries that are being charged by a generator that's 50 or 100 yards away from your regular setup, and your station is still considered to be battery powered in that case. So you still get all the points for running a alternate power station. That's because your generator is not directly connected to your station. So that was an interesting uh, loophole in the rules that I found out about while I was reading up on that. So very interesting. You do get more points for running your station on alternate power sources. So if you can run without a generator, when they say alternate power, they mean something that's not burning fuel to produce the power. And the rules also include things like you could run your lights off of the generator, but not your radio or something like that, right? So those are all things to consider if you're really into that whole field day contesting thing.
So if I can prove to the ARRL that my grid tied system is running from a nuclear power plant,
that's not a fossil fuel usage. So yeah,
that's right. There you go.
Or they have all those windmills down there by Price or by the mouth of the canyon leading, on Highway 40.
Oh
So
yeah.
I know you can say to the power company, hey, I'll pay extra if you only give me power that was generated from the wind
Right.
generators, right? And they'll say, sure, pay us extra. We'll guarantee that your power is only coming from those windmills. You betcha. Yeah. Now, whether it actually is or not is immaterial because it's all numbers, right? It's just
Yep.
how the numbers add up. But they're happy to say that, and if
Well,
that's the case, well, hey, there you go. It's purely renewable power.
speaking of which, if you're talking about that wind farm, especially going down to Price, a Highway 6.
Yeah, that's the one I'm thinking of. Highway 6.
Yeah, there's a lot of different type of wind powered windmills, if you will. So it's worth just taking a look because they don't have, they have the really large ones with the 300-foot blades and even larger than that, but they also have ones that are cylindrical. And I mean, the YouTube is full of different types of wind generators. You can do it yourself type of thing. And they use, they cut 55 gallon drums in half, and they, put those,
Yep.
mount those to a shaft. And, there's some really interesting ways you can, I mean, the object of the game is to spin that dial, right?
Yep.
To get that axis rotating, and lots of ways of doing that. So very interesting.
Yeah, there are a lot of clever ways to take advantage of those renewable power resources like solar and wind. And I think a lot of people think, well, I'm going to go with solar and I'm going to invest in that, and that's the only thing I'm going to use. And it may be a good idea to fold in a little wind power generator on the side. Just to have that extra source of power that's always there when the wind's blowing. Don't depend solely on one technology.
I'm actually going to get one of those wind-powered turbines and put it next to one of my generators that really suck. So I should have power all the time, even at night. That was a joke, guys.
Yeah.
Tough crowd.
Tough crowd. Yeah. All right. Well, if we're done, then no more questions. I'm going to go ahead and stop recording, and I will put this video up on the site as soon as it gets converted.
Thank you very much, Jan, for a